The world around you is quiet. The sky above you looks peaceful. Stars are scattered across the darkness like tiny sparks frozen in place. Somewhere in that sky, the planets move silently along their ancient paths. Mercury, Venus, Mars, Jupiter, Saturn, worlds humans have watched for thousands of years. And far beyond what the naked eye can easily see, Uranus and Neptune continue their slow journey around the Sun. From Earth, the solar system feels familiar. It feels mapped. It feels complete. We grow up learning the names of the planets like a simple list. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. 8 planets orbiting the Sun. 4 rocky planets close in. 4 giant planets farther out. Then Pluto, once called the 9th planet, now classified as a dwarf planet. And after that, most people imagine only darkness. But that picture is not the full truth. The solar system is not a neat classroom diagram. It is not a clean line of planets printed on a poster. It is not a simple family of 8 worlds floating peacefully in empty space. The real solar system is far bigger, far darker, and far more mysterious than most people ever realize. Beyond Neptune, the sun's light becomes weak. The warmth that makes Earth alive fades into almost nothing. The planets we know are left behind. The darkness grows deeper. The distances become difficult for the human mind to understand. And out there, in the frozen frontier beyond Neptune, scientists are finding clues that something may not be right. Something may be pulling on the outer solar system. Something may be disturbing the distant Kuiper Belt. Something may be hiding in the darkness. Not Planet 9, the famous hypothetical giant planet that scientists have discussed for years. This is something different. Smaller. Stranger. Possibly rocky. Possibly closer than the classic Planet 9 idea, a hidden world that has not yet been photographed, not yet confirmed, not yet named, but may already be leaving its gravitational fingerprint on distant icy objects. For now, some people refer to this possible object as Planet Y. But before we go deeper, one thing must be clear. Planet Y is not a confirmed planet. No telescope has taken a clear image of it. No spacecraft has visited it. No space agency has officially announced that a new planet has been discovered. Right now, Planet Y is a hypothesis, a possible explanation for a strange pattern in the outer solar system. But many great discoveries begin exactly like this. Not with a clear picture, not with a direct sighting, but with something that does not fit. A strange movement, a tilted orbit, a missing piece. A gravitational clue. That is how Neptune entered human knowledge. Astronomers noticed that Uranus was not moving exactly as expected. The planet's orbit had small irregularities. Instead of assuming the laws of gravity were wrong, scientists asked a different question. What if another unseen planet is pulling on Uranus? They calculated where that planet should be. Then they looked. And there it was. Neptune, a world discovered first by mathematics, then by telescope. Planet Y may or may not follow a similar path. The evidence is not yet as strong as it was for Neptune. The mystery is still developing, but the principle is the same. Sometimes we discover a planet not by seeing the planet itself, but by noticing what its gravity does to everything around it. That is what makes this story so fascinating. Because if Planet Y exists, it may have been there for billions of years. While Earth formed oceans, Planet Y may have already been frozen in darkness. While life began in Earth's ancient seas, Planet Y may have circled silently beyond Neptune. While dinosaurs walked under a warm sun, Planet Y may have moved through the outer solar system under a black sky. While humans built the first telescopes and began mapping the heavens, Planet Y may have remained hidden, too dim and too distant for us to notice. And even today, with all our technology, with space telescopes, supercomputers, planetary probes, and massive sky surveys, it may still be hiding. That should make us humble, because we often think our own solar system is known territory. We talk about distant galaxies, black holes, exoplanets, and the edge of the observable universe, but our own cosmic backyard may still contain secrets large enough to change textbooks. Think about that. We have sent spacecraft to every major planet. We have landed on Mars. We have photographed Pluto. We have flown past Jupiter's storms, Saturn's rings, Uranus's pale atmosphere, and Neptune's deep blue world. We have tracked comets, mapped asteroids, and discovered thousands of objects beyond Neptune. And still, an entire planet may be missing from our map. That is the power of the outer solar system. It is not empty. It is not simple. It is not finished. It is a dark frontier. a place where sunlight fades, temperatures collapse, and time moves on scales far beyond human experience. To understand Planet Y, we need to understand what lies beyond Neptune. Neptune orbits the Sun at about 30 times the distance between Earth and the Sun. That distance is called 30 astronomical units, or 30 AU. 1 AU is the average distance from Earth to the Sun. So when we say Neptune is 30 AU away, we mean it is 30 times farther from the Sun than Earth. From Earth, sunlight is powerful. It warms the oceans, drives the weather, feeds plants, and supports nearly all life. But at Neptune, sunlight is already about 900 times weaker than it is here. The Sun still shines, but it is no longer the overwhelming blazing disk we know from Earth. Beyond Neptune, the Sun becomes even weaker. At 50 AU, sunlight is 2,500 times weaker than on Earth. At 100 AU, it is 10,000 times weaker. At 200 AU, it is 40,000 times weaker. Out there, daylight is not daylight as we understand it. The Sun is still the brightest object in the sky, but it becomes a distant, brilliant star. It can illuminate a surface faintly, but it cannot bring warmth in the earthly sense. This is the region where ancient icy bodies live. This is where the Kuiper Belt begins. The Kuiper Belt is a huge region beyond Neptune, filled with icy objects, dwarf planets, frozen fragments, and leftovers from the birth of the solar system. Pluto is part of this region. So are Eris, Haumea, Makemake, and many smaller worlds most people have never heard of. For a long time, Pluto seemed like a lonely outpost. But when astronomers discovered more objects beyond Neptune, they realized Pluto was not alone at all. It was part of a vast population. The outer solar system was not empty. It was crowded with ancient frozen bodies. And these bodies are important because they are leftovers. They are pieces of the original material that formed the planets. They are like cosmic fossils. By studying them, scientists can learn what the early solar system was like before planets finished forming, before the system became stable, before Earth became the world we know. But recently, some of these distant objects may be telling us something else. They may be revealing that the outer solar system is warped, not visibly warped like a bent metal sheet, not dramatically twisted like something from science fiction, but subtly tilted in a way that may require explanation. And one possible explanation is Planet Y, a hidden planet, a small world far beyond Neptune, a body whose gravity may be slowly bending the orbits of distant objects. If this is true, then Planet Y is not just another planet. It is a clue to the solar system's violent past, because a rocky planet in the outer solar system would be strange. The rocky planets are supposed to be close to the Sun. Mercury, Venus, Earth, and Mars all formed in the inner region where it was hot enough that only rock and metal could easily survive as solids. Farther out, ice became abundant and planets grew larger. That is why the outer planets became giants. So if Planet Y is rocky, how did it get so far away? There are several possibilities. Maybe it formed near the Sun and was thrown outward during the chaotic youth of the solar system. A close encounter with Jupiter or Saturn could have acted like a gravitational slingshot, launching a small, rocky world into the outer darkness. Maybe Planet Y formed farther out through some unusual process we do not fully understand. Or maybe the strangest possibility is true. Planet Y may be a captured rogue planet. A rogue planet is a planet without a star. It drifts through interstellar space, alone in the darkness. It may have formed around another star and then been thrown away by gravitational interactions. Most rogue planets wander forever, but rarely, under the right conditions, a star may capture one. If Planet Y is a captured rogue planet, then it did not begin in our solar system. It would be an alien world inside our own system. Not alien in the sense of life or civilization, but alien in origin. A planet born around another star now orbiting our Sun. That possibility is breathtaking. It would mean that by studying Planet Y, we might be studying a world from another planetary system without ever leaving our own. But all of this depends on one thing. We have to find it. And that is incredibly difficult. A planet beyond Neptune reflects almost no sunlight. If it is small, dark, and distant, it would appear as a tiny faint point among countless stars and galaxies. It would move slowly across the sky, so slowly that it could be mistaken for a background object unless astronomers compare images taken over long periods. This is why Planet Y may have remained hidden, not because it is impossible to see, but because it is faint, distant, slow, and lost in an enormous sky. Finding it would require patience, repeated sky surveys, powerful telescopes, careful data analysis, and maybe a little luck. But if one day astronomers detect a faint moving object at the right distance, with the right orbit and the right mass, the discovery would be historic. The solar system would change, the map would change, the story would change, and humanity would be reminded again that the universe still has secrets, even here, even close to home, even in our own solar system. Somewhere beyond Neptune, in the darkness where sunlight is almost gone, a hidden world may be moving silently. A planet without a name, a planet without a photograph, a planet that may have been waiting for billions of years. And if Planet Y is real, then the solar system is not finished revealing itself. It is still hiding worlds, it is still keeping secrets, and we are still only beginning to understand the place we call home. To understand the mystery of Planet Y, we have to travel beyond Neptune. Not physically, but mentally. We have to leave behind the familiar solar system. Leave behind Earth's blue sky. Leave behind Mars, Jupiter, Saturn, Uranus, and Neptune. We have to keep moving outward until the sun becomes small, the light becomes weak, and space becomes cold beyond imagination. This is where the Kuiper Belt begins. The Kuiper Belt is one of the most important regions in the solar system, but most people barely understand what it is. Many people know Pluto is out there. Some know there are icy objects beyond Neptune, but the Kuiper Belt is much more than a collection of frozen leftovers. It is a preserved record of the solar system's birth. It is a frozen archive. It is a cosmic museum of ancient material. When the solar system formed about 4.5 billion years ago, it began as a vast cloud of gas and dust. Gravity pulled that cloud inward. The center became the sun. Around the young sun, the remaining material flattened into a spinning disk. Inside that disk, planets began to form. Small particles stuck together. Dust became pebbles. Pebbles became rocks. Rocks became planetesimals. Planetesimals became planetary embryos. And eventually, planets were born. But not all material became planets. Some pieces remained small. Some were scattered. Some were trapped in stable regions. Some became asteroids. Some became comets. Some became icy bodies beyond Neptune. That distant leftover material is what we now call the Kuiper Belt. In a way, the Kuiper Belt is made of the pieces that did not become planets. But that does not make them unimportant. Actually, it makes them extremely important. Because planets change, Earth has changed dramatically since its formation. Plate tectonics recycle the crust. Weather erodes mountains. Oceans reshape coastlines. Life changes the atmosphere. Volcanoes cover old surfaces with new rock. Much of Earth's earliest history has been erased, but many Kuiper Belt objects are different. A distant object at 100 AU may take roughly 1,000 years or more to orbit the Sun, depending on its exact path. At 200 AU, an orbit can take thousands of years. Human civilization is young compared with one orbit of such an object. This is why studying the outer solar system requires patience. We cannot simply watch a full orbit and understand everything. We must observe a tiny piece of motion and use mathematics to reconstruct the rest. This makes discoveries difficult, but also powerful. Every faint object found beyond Neptune adds a new data point. Every orbit measured improves the map. Every strange pattern challenges our models, and sometimes one pattern can change everything. The Kuiper Belt is also scientifically important because it connects our solar system to exoplanet systems. Around other stars, astronomers have found debris disks, asteroid belts, and signs of planet formation. Our Kuiper Belt is a nearby example of such a structure. By studying it in detail, we learn how planetary systems evolve after planets form. If Planet Y exists, it would show that even our own solar system has a hidden complexity we did not fully appreciate. It would also suggest that distant planetary systems might hide similar unseen worlds shaping debris belts around other stars. The search for Planet Y is therefore not only about finding one object. It is about understanding how planets sculpt the architecture of their systems. It is about learning how hidden masses influence visible debris. It is about reading the structure of a planetary system the way a detective reads a crime scene. The Kuiper Belt is that crime scene. It contains the evidence. The question is whether Planet Y is the hidden suspect. Imagine a cinematic view of this region. The camera leaves Neptune behind. The blue planet slowly shrinks into the darkness. Its moon Triton becomes a faint point. The sun is far behind, no longer a blazing disk, but a harsh, distant light. The camera moves outward. Frozen objects drift past. Some are reddish and dark. Some are covered in bright ice. Some rotate slowly. Some have tiny moons. Some move in pairs, locked together by gravity. The silence is total. There is no air, no wind, no sound, only motion. ancient motion. Then the camera pulls back farther and farther until the orbits of many objects become visible. Most follow a broad disk, but in the distant region, something seems slightly off. The plane appears to bend. The outer objects do not sit exactly where expected. The camera searches the darkness. Nothing obvious appears, but the orbits whisper a possibility. Something may be there. That is the mystery. The Kuiper Belt may be showing us the shadow of a hidden planet, not a shadow made of light. A gravitational shadow, a pattern, a bend, a clue. And this is why the Kuiper Belt is not just the frozen edge of the solar system. It is a message from the past. It is a map of invisible forces. It is the place where the story of Planet Y begins. Before we can understand the hidden planet, we have to understand the belt it may be warping. Because Planet Y, if real, is not isolated. It belongs to a larger mystery. A mystery written in the frozen debris beyond Neptune. A mystery that asks whether the solar system's outer edge is being shaped by a world we have never seen. And if the answer is yes, then the Kuiper Belt is not just an archive. It is a warning, a sign that the solar system is still hiding something major, a sign that the map is incomplete, a sign that beyond Neptune, in the cold and ancient dark, another planet may be waiting. Sometimes the universe does not reveal its secrets directly. It does not always show us a planet. It does not always give us a clear image. It does not always place the answer in front of a telescope. Sometimes the universe only leaves a pattern, a small distortion, a strange movement, a tiny mismatch between what should happen and what actually happens. That is where the mystery of Planet Y becomes serious. Because astronomers are not simply imagining a hidden planet beyond Neptune, they are responding to something unusual in the distant solar system. A possible warp, a bend, a tilt in the orbital structure of faraway icy objects. To understand why this matters, imagine the solar system as a giant spinning disk. The sun formed at the center of a rotating cloud of gas and dust. Around it, a flattened disk of material began to spin. Inside that disk, small particles collided. Dust became pebbles. Pebbles became rocks. Rocks became larger bodies. And over millions of years, planets were born. Because everything formed from the same rotating disk, most objects in the solar system should orbit in roughly the same plane. Not perfectly, but roughly. Mercury is slightly tilted. Pluto is more tilted. Some comets have extremely strange orbits, but the main planets still follow a broad, flat structure. This is why every solar system diagram shows the planets moving almost like they are on invisible tracks around the sun. That flatness is not random. It is a fossil from the birth of the solar system. It is the memory of the ancient disk that created everything. So when distant objects beyond Neptune appear to lean away from that expected plane, astronomers pay attention. Because a tilted pattern may mean something pulled them. And in space, the thing that pulls is gravity. One object with a strange orbit is not enough. One object can be an accident. One object can be scattered by Neptune. One object can be affected by a collision. One object can have a strange orbit simply because the solar system is messy. But when a group of objects begins to show a related tilt, that becomes harder to dismiss. It begins to look like a structure, and structure demands an explanation. That is the foundation of the Planet Y mystery. Scientists studying distant Kuiper Belt objects noticed that some of them may not be orbiting in the exact plane expected from the known planets. Instead, their average orbital plane appears slightly warped, not violently twisted, not obviously broken, but shifted enough to raise a question. Why? Why would the distant Kuiper Belt lean? Why would icy objects beyond Neptune follow a plane that does not perfectly match the inner solar system? Could Neptune be responsible? Maybe. Neptune is the strongest known gravitational force in that region. It has shaped the Kuiper Belt for billions of years. It controls resonances. It scatters icy bodies. It helped organize the outer solar system after the giant planets migrated. But Neptune alone may not explain the full pattern. Could Pluto be responsible? No, Pluto is far too small. Could Eris or another dwarf planet cause it? Again, probably not enough. Could it be observational bias? That is possible. And scientists take that seriously. Astronomy is not perfect. We do not observe the sky evenly. Some regions are studied more deeply than others. Some objects are easier to detect because they are brighter. Others remain invisible because they are darker, smaller, or located in crowded star fields. So any claim about a distant warp must be tested carefully. But if the warp is real, then one explanation becomes especially interesting. A hidden planet, a small world beyond Neptune, orbiting at an inclined angle, slowly pulling the distant Kuiper Belt out of shape. This is the kind of idea that sounds dramatic, but it is based on a simple principle. Gravity does not need to be loud. Gravity only needs time. A hidden planet would not suddenly grab the Kuiper Belt and bend it overnight. It would not create a visible wave like a hand-pushing cloth. Instead, it would act slowly. Orbit after orbit, century after century, million years after million years, each small gravitational tug would be tiny, almost nothing. But over hundreds of millions of years, tiny changes add up. This is how the architecture of the solar system changes, not always through explosions, not always through collisions, sometimes through patience. A planet hidden in darkness could slowly sculpt the orbits around it. This is why Planet Y is such a fascinating possibility. It may be invisible to us right now. But if it exists, its gravity may already be visible in the motion of other objects. That is the key. We may not have seen the planet, but we may be seeing its fingerprint. Astronomers use computer simulations to test this kind of idea. They create a virtual solar system. They add the Sun. They add Jupiter, Saturn, Uranus, and Neptune. They add known distant objects. Then they test different scenarios. What happens if there is no hidden planet? What happens if Neptune alone controls the region? What happens if a passing star disturbed the outer solar system long ago? What happens if a small planet exists beyond Neptune? What mass would it need? What distance? What orbital tilt? What shape of orbit? Then they let the simulation run forward through huge spans of time. Millions of years. Hundreds of millions of years. Sometimes billions. They compare the result with what astronomers actually observe. Most possibilities do not work. Some create no warp. Some create the wrong kind of warp. Some make the objects too scattered. Some destroy the pattern entirely. But certain models with a hidden planet can produce a distant tilt similar to what may be observed. That does not prove Planet Y exists, but it makes the idea worth investigating. And this is how science moves forward, not by guessing blindly, but by asking which explanation best matches the evidence. The important thing is that Planet Y is still only a hypothesis. It is not confirmed. A hypothesis is not a fact. It is a possible explanation. A serious one, maybe. An exciting one, definitely, but still unproven. That uncertainty actually makes the story more powerful, because we are watching science happen in real time. We are not looking back at a discovery after everything is settled. We are standing in the middle of the mystery. The clues are on the table. The answer is not yet known, and somewhere beyond Neptune, the darkness may be hiding the missing piece. Imagine being an astronomer studying the far outer solar system. You are not looking at beautiful close-up images like the pictures of Mars or Jupiter. You are looking at faint points of light, tiny dots, numbers, positions, angles, orbital elements. You are working with objects so far away that sunlight takes many hours to reach them. You are trying to understand a region where one orbit can take hundreds or thousands of years. Then you notice something. The dots are not random. Their orbits may be leaning. The belt may be warped. At first you doubt it. Maybe the data is incomplete. Maybe the sample is too small. Maybe the survey missed objects in certain areas. Maybe the result will disappear when more data comes in. So you test it. You run simulations. You compare models. You remove certain objects. You add new ones. You check assumptions. You ask other scientists to look, and the possibility remains. Maybe there is another planet. That is the moment when the mystery becomes real. Not because the answer is proven, but because the question refuses to disappear. Planet Y, if it exists, would be like an invisible hand pressing on the distant solar system. Its gravity would pull on icy objects. Its inclined orbit would twist their average plane. Its long presence would leave a signature written across billions of miles. And the strangest thing is this. Planet Y might have been doing this for almost the entire history of the solar system. While Earth formed oceans, Planet Y may have already been moving in darkness. While life began, Planet Y may have been frozen and silent. While dinosaurs ruled Earth, Planet Y may have been tugging slowly on the Kuiper Belt. While humans built the first telescopes, Planet Y may have remained unseen. While we discovered Uranus, Neptune, Pluto, and thousands of Kuiper Belt objects, Planet Y may still have been there, waiting, not hiding intentionally, not mysterious by choice, just too far, too faint, too cold, too dark, and too slow. This is what makes outer solar system science so humbling. The solar system is our home, but we still do not know all of it. We have lived under this sky for thousands of years. We have named the planets. We have sent spacecraft to distant worlds. We have mapped the Moon and Mars. We have photographed Pluto. And still, a planet may be missing from our map. The warp in the Kuiper Belt is not just a scientific detail, it is a reminder that nature is bigger than our diagrams, a reminder that our maps are always incomplete, a reminder that even familiar places can hide unknown worlds. And if Planet Y is eventually discovered, the warp may become one of the most important clues in modern astronomy. Just like Uranus's strange motion led to Neptune, just like Pluto's faint movement revealed a new world in 1930, just like exoplanet wobbles revealed planets around other stars, a small anomaly can become a revolution. That is how discovery often begins, with something that does not fit, a tiny error, a strange tilt, a pattern in the dark. And right now, beyond Neptune, that pattern may be telling us something extraordinary. There may be a planet out there, a dark rocky world, a hidden sculptor, a silent mass pulling on ancient ice, and until we find it, the outer solar system remains unfinished. The map still has a blank space, and in that blank space, Planet Y may be waiting. Before we go any deeper into this mystery, we need to clear up one of the biggest confusions surrounding hidden planets beyond Neptune. Planet Y is not Planet 9. These two ideas are often mixed together because both involve the same dark region beyond Neptune. Both involve a possible unseen planet. Both involve strange patterns in the orbits of distant objects. Both sound like they belong in the same story, but scientifically, they are different mysteries. Planet 9 is the more famous idea. For years, astronomers have discussed the possibility that a large hidden planet may exist far beyond Neptune. This possible planet was suggested because some extremely distant trans-Neptunian objects appeared to have unusual orbital alignments. Their orbits were stretched. Their paths were distant. Some seemed to point in similar directions, as if something massive was shaping them from far away. That possible hidden object became known as Planet 9. If Planet 9 exists, it would probably be much larger than Earth. It might be several times Earth's mass. It might be a super-Earth or a mini-Neptune, a kind of planet that is common around other stars but missing from the inner part of our own solar system. Planet 9 would also likely be extremely far from the Sun, hundreds of astronomical units away, possibly so far that one orbit around the Sun could take thousands or even tens of thousands of years. That makes Planet 9 very difficult to find. It would receive almost no sunlight. It would reflect very little light back to Earth. It would move very slowly against the background stars. Even if it is real, it could remain hidden for a long time. Planet Y is different. Planet Y is not mainly proposed because of the same extreme orbital clustering associated with Planet 9. Planet Y is connected to a possible warp in the distant Kuiper Belt. Its possible mass may be much smaller, maybe somewhere between Mercury and Earth. Its possible orbit may be closer than the extreme Planet 9 scenario, though still far beyond Neptune. And most importantly, Planet Y may be rocky. That is what makes it so strange. Because a rocky world in the outer solar system does not fit the simple pattern we expect. The solar system has two obvious planetary zones. The inner zone contains the rocky worlds: Mercury, Venus, Earth, Mars. These are small, dense planets made mostly of rock and metal. The outer zone contains the giants. Jupiter and Saturn are gas giants. Uranus and Neptune are ice giants. This arrangement makes sense because of the way the solar system formed. Near the young sun, temperatures were high. Ice could not easily survive as solid material. Only rock and metal could condense and build planets. That is why the inner planets became rocky. Farther out, beyond the ice line, temperatures were lower. Water ice, methane ice, ammonia ice, and other frozen materials could exist. Suddenly, there was much more solid material available. Planets could grow larger. Some became massive enough to capture thick atmospheres. That is how the outer giants formed. So if Planet Y is a small rocky planet beyond Neptune, it is out of place. It is like finding a desert stone at the bottom of an ocean. It does not belong there according to the simple story. And whenever nature gives us something that does not belong, science becomes interesting. Because exceptions are not mistakes. Exceptions are messages. They tell us our models are incomplete. They tell us there is more history than we understood. They tell us that the solar system may have been more violent, more chaotic, and more dynamic than the clean diagrams suggest. Planet 9 would be mysterious because it may be huge and distant. Planet Y would be mysterious because it may be small, rocky, and misplaced. That difference matters. Planet 9 may tell us about the deep outer solar system and the behavior of extreme distant objects. Planet Y may tell us about the solar system's early violence, planetary scattering, hidden rocky worlds, and the possibility that a planet formed in one region but now lives in another. One is a possible distant giant, the other may be a lost rocky survivor, and there is another reason this distinction matters. The evidence is different. Planet 9 is linked to the strange clustering of the orbits of some extremely distant objects. Planet Y is linked to a possible tilt or warp in the average plane of Kuiper Belt objects. These are different clues, and different clues require different explanations. A scientist cannot simply combine every outer solar system mystery into one hidden planet and call the case solved. That would be too easy. The outer solar system is complicated. Different patterns may have different causes. Some may be real. Some may be statistical artifacts. Some may come from observational bias. Some may be caused by known planets. Some may point toward unseen objects. This is why scientists are careful. They ask, what exactly is the anomaly? Which objects show it? How strong is the signal? Could our surveys be biased? Could Neptune explain it? Could known dwarf planets explain it? Could a passing star have caused it? Could a swarm of smaller bodies create the same effect? Or does a hidden planet fit best? That careful questioning is what separates science from speculation. Planet Y is exciting, but excitement is not proof. It is a hypothesis, a possibility, a shadow in the data, but shadows matter when they keep appearing in the right place. Imagine walking through a dark house. You do not see anyone, but you hear a floorboard creak, then another, then you notice a door moving slightly. You still cannot say with certainty that someone is inside, but you can say something is happening. You investigate. That is what astronomers are doing with Planet Y. They are not claiming the hidden world has been found. They are investigating why the outer solar system may be behaving strangely, and the deeper they look, the more important the distinction becomes. Planet 9 may be a massive unseen planet shaping extreme objects far away. Planet Y may be a smaller unseen planet warping a different region. Both are possible, neither is confirmed. But either one, if discovered, would change astronomy. Now imagine if both were real. The solar system would become far more complex than our current textbooks suggest. Instead of 8 planets followed by scattered debris, there could be multiple hidden planetary bodies beyond Neptune. Some small, some large, some icy, some rocky, some native to the solar system. Maybe one even captured from another star. That would transform our understanding of the outer solar system from a cold debris field into a deep planetary frontier. But even if only Planet Y exists, the consequences would be enormous, because a rocky planet beyond Neptune forces us to ask, where did it form? How did it survive? Why is it there? And what else have we missed? A hidden rocky planet would be a relic, a survivor, possibly a world thrown away during the solar system's violent youth. That idea brings us to one of the most important parts of the story. How could a rocky planet end up beyond Neptune in the first place? Because if Planet Y is real, its location is not just a fact, it is a clue to its origin, a clue to its history, a clue to the chaos that shaped everything we now call home. If Planet Y exists, one question becomes more important than almost everything else. How did it get there? Because a rocky planet beyond Neptune is not supposed to be there in the simple version of solar system history. The inner solar system belongs to rock. The outer solar system belongs to giants, ice, and frozen debris. That is the pattern. But Planet Y may break that pattern. And when a planet breaks the pattern, it becomes a key to a hidden story. To understand that story, we need to go back to the beginning. About 4.5 billion years ago, the solar system was not a calm family of planets. It was a huge rotating disk of gas and dust around a young sun. Everything was in motion. Everything was colliding. Everything was growing, breaking, merging, and shifting. The planets did not appear fully formed. They were built. Dust particles stuck together. Tiny grains became pebbles. Pebbles became rocks. Rocks became larger bodies. Larger bodies became planetesimals. Planetesimals collided and merged into planetary embryos. Some of those embryos became planets. Others were destroyed. Others were swallowed. Others were thrown away. The early solar system was not peaceful. It was a battlefield of gravity. In the inner solar system, rocky planetary embryos grew from metal and silicate material. There may have been more of them than the 4 rocky planets we see today. Earth, Venus, Mars, and Mercury may be only the survivors of a much larger early population. Some embryos collided with each other. Some merged into larger planets. Some were shattered. Some were thrown into new orbits. and some may have been ejected from the inner solar system entirely. This is where Planet Y may enter the story. Imagine a young rocky world, smaller than Earth but large enough to become round under its own gravity. It formed in the inner solar system, perhaps near the region where Earth and Mars were growing. It had rock, metal, maybe internal heat, maybe a thin early atmosphere. It was not a finished planet like Earth, but it was a real world. Then, the giant planets began to reshape the solar system. Jupiter and Saturn were not just sitting quietly where they are today. In the early solar system, the giant planets likely migrated. Their gravity interacted with the disk of smaller bodies around them. As they moved, they disturbed everything nearby. Jupiter especially was a monster of gravity. It is more massive than all the other planets combined. A close encounter with Jupiter can completely rewrite an object's orbit. If a small rocky planet passed near Jupiter, the encounter could act like a gravitational slingshot. The small planet would fall toward Jupiter, gain speed, and then be thrown away onto a new path. Depending on the angle and velocity, many things could happen. It could crash into Jupiter. It could be thrown into the Sun. It could collide with another planet. It could be ejected from the solar system forever. Or, under the right conditions, it could be launched into a distant orbit but remain bound to the Sun. That survivor could become Planet Y, a rocky planet born closer to the Sun, then exiled into the outer darkness. This is not magic. It is orbital dynamics. Gravity can throw worlds across a solar system. We already know that smaller bodies are scattered by giant planets. Comets can be redirected. Asteroids can be moved. Distant objects can be pushed into new orbits. The early solar system was full of such events. So a rocky world being thrown outward is not impossible. It would be rare. It would require the right encounter. It would require the world to survive. But rare does not mean unreal. The solar system has had 4.5 billion years to produce rare outcomes, and Planet Y may be one of them. If this scenario is correct, Planet Y would be a frozen exile, a lost sibling of the inner planets, a world that began in the warmth and violence of the young inner solar system but ended up in a cold orbit far beyond Neptune. This would make Planet Y incredibly valuable scientifically, because Earth has changed too much to preserve all of its earliest history. Plate tectonics recycle Earth's crust. Weather and water erase ancient surfaces. Life itself has changed Earth's atmosphere and chemistry. Mars preserves more ancient history, but it has also changed. Mercury preserves ancient craters, but it formed very close to the Sun and has its own extreme environment. Planet Y, if scattered early, may have frozen its history in place. It could be a preserved rocky embryo from the solar system's formation era, a planetary time capsule, a world that stopped evolving normally because it was thrown into a deep freeze. Studying it would be like studying a missing piece of the inner solar system's past. Its density could reveal how much metal it contains. Its surface composition could show where it formed. Its crater record could show how much bombardment it experienced. Its possible moons could reveal whether it suffered impacts or captures. Every measurement would tell part of its story. But scattering from the inner solar system is not the only possibility. There is a second possibility. Planet Y may have formed far from the Sun. At first, this sounds unlikely. A rocky planet forming beyond Neptune does not fit the usual model. The outer solar system was cold, rich in ice, and filled with materials that should have produced icy bodies rather than purely rocky planets. But planet formation is not always simple. The early solar system was messy. Material moved, objects migrated, impacts stripped layers away, bodies captured and lost mass. Some rocky material from the inner solar system could have been scattered outward early and later collected. Some icy bodies could have lost volatile material through collisions or other processes, leaving behind denser rocky cores. Maybe Planet Y formed from an unusual concentration of rocky material. Maybe it began as an icy rocky body and later lost much of its ice. Maybe our models of outer solar system formation are missing a pathway for building dense bodies in distant regions. This possibility is more speculative, but it cannot be dismissed automatically. Science must remain open to uncomfortable possibilities, especially when nature has repeatedly shown that planets can surprise us. When astronomers began finding planets around other stars, many of them did not match expectations. Hot Jupiters were discovered orbiting extremely close to their stars. Super-Earths were found in huge numbers. Mini-Neptunes appeared everywhere. Some planets orbited 2 stars. Some planets had extremely stretched orbits. Some systems were packed with several planets close to their stars. The universe did not build planetary systems according to our early expectations. So maybe the solar system also has a hidden exception. Maybe Planet Y formed far out through a process we have not fully understood. If so, it would force scientists to revise models of planet formation. But there is a third possibility, and it is the strangest of all. Planet Y may not have formed in our solar system. It may be a captured rogue planet. A rogue planet is a planet without a star. Imagine a world drifting through the galaxy alone. No sunrise, no seasons, no parent star, no familiar orbit, just a frozen body moving through interstellar darkness. These planets may be more common than people once imagined. Some are likely born around stars and later ejected by gravitational interactions. Others may form directly from collapsing gas clouds, like tiny failed stars. Most rogue planets wander forever. They pass between stars. They remain dark. They are extremely difficult to detect because they do not reflect light from a nearby sun. But if one passed near a young solar system under the right conditions, it could be captured. Capture is not easy. A planet flying past the sun would normally enter and leave again. The sun's gravity would bend its path, but not hold it permanently. For capture to happen, the rogue planet must lose energy. That could happen if it interacted with the sun's early disk of gas and dust. It could happen if it passed near a giant planet and had its orbit altered. It could happen through complex gravitational interactions involving moons or other bodies. Rare? Yes. Impossible? No. If Planet Y is a captured rogue planet, then it is not just a hidden planet. It is an alien world inside our solar system. Not alien because of life, alien because of origin. A world born around another star. A world thrown into the galaxy. A world captured by our sun. A world that has been hiding beyond Neptune for billions of years. That possibility is almost poetic. Somewhere in the galaxy, a star may have lost a planet. That planet may have wandered alone through darkness. Then our sun may have captured it, and now it may be part of our solar system. If that is true, Planet Y would be one of the most important discoveries in planetary science, because it would let us study an extrasolar planet up close, not by sending a spacecraft light years away, but by studying a foreign world that came to us. How would scientists know? They would look for clues. The first clue would be the orbit. A planet formed in the solar system and scattered outward may have an orbit that still reflects interactions with the known planets. It may be inclined, it may be stretched, but its path may still make sense within solar system dynamics. A captured object could have a more unusual orbit. It might be highly inclined, it might be extremely eccentric, it might even orbit in a direction unlike the major planets. The second clue would be composition. If Planet Y is made of material similar to the terrestrial planets, it may have formed near the sun. If it has more ice, maybe it formed farther out. If it has isotope ratios that do not match solar system material, that would be extraordinary. Isotope ratios are like fingerprints. They can reveal where material came from. A world from another star might carry a different chemical signature. The third clue would be moons. Moons are witnesses. If Planet Y has moons, their orbits and compositions could reveal whether they formed with the planet, were captured later, or were created by impacts. A moon system could help determine Planet Y's mass. It could reveal its history. It could show whether the planet has experienced violent events. Moons would be more than companions. They would be evidence. Now imagine each origin story like a different film. In the first film, Planet Y is born near the sun. It grows in the same violent nursery that formed Earth and Mars. Then Jupiter throws it outward. It becomes an exile, frozen forever in the outer darkness. In the second film, Planet Y forms far from the sun in an unusual pocket of material. It becomes a strange native of the deep solar system, challenging our theories of planet formation. In the third film, Planet Y is born around another star. It is thrown into interstellar space. It wanders alone until the young sun captures it. It becomes a foreign planet hidden inside our own solar system. All three stories are powerful. All three are possible in principle. And all three would change how we understand planets. That is why Planet Y matters. It is not just about whether there is another dot on the solar system map. It is about history. It is about violence. It is about survival. It is about lost worlds. The planets we see today are not necessarily the only planets that ever belonged to the solar system. They are the survivors, the stable ones, the ones that remained visible and familiar, but there may have been others. Worlds that collided, worlds that shattered, worlds that fell into the sun, worlds that were thrown into interstellar space, and maybe one world that was thrown outward but not lost. A world that became Planet Y. The idea is haunting. because it means the solar system is not just a family of planets. It is a history of winners, losers, survivors, and ghosts. Planet Y, if real, may be one of those ghosts. A planet that should have been gone. A planet that nearly escaped. A planet that ended up in the cold far beyond Neptune. And now, billions of years later, we may be noticing its presence not because we see it, but because other distant objects still feel its gravity. That is the kind of story only astronomy can tell. A hidden world, an ancient exile, a frozen clue to the violent birth of everything we know. Now imagine that Planet Y is real. Imagine that one day, after years of searching, astronomers finally detect it. At first, it is nothing more than a faint moving point of light, a tiny dot shifting slowly against the background stars. The discovery is confirmed. The orbit is calculated, the distance is measured, the object is real. A new world has been found beyond Neptune. But after the excitement, a new question begins. What is it like? What would Planet Y actually look like? To answer that, we have to travel in imagination to the far outer solar system. Leave Earth behind, leave the Moon, pass Mars, cross the asteroid belt, move beyond Jupiter's storms, beyond Saturn's rings, beyond Uranus, beyond Neptune. Keep going. The sun shrinks behind you, the light fades, the warmth disappears, the planets become memories. And finally, far in the frozen darkness, Planet Y appears. At first, it is just a black shape against a black sky. Then the faint sunlight reveals the surface. A rocky world, frozen, silent, ancient. If Planet Y is between Mercury and Earth in mass, it could have enough gravity to be round. It may have a solid surface. It may have mountains, craters, cliffs, plains, and ancient impact basins, but it would not look like Earth. There would be no blue oceans, no white clouds, no green continents, no glowing cities, no weather systems swirling through a living atmosphere. Planet Y would likely be a world of darkness and ice. At its distance from the Sun, light would be extremely weak. The Sun would still be the brightest object in the sky, but it would no longer look like the huge blazing disk we see from Earth. It would look smaller, sharper, more like an intensely bright star. It might still cast faint shadows, but those shadows would be weak. The sunlight would not carry meaningful warmth. The surface would be brutally cold, not winter cold, not polar cold, not the cold of Antarctica, something far beyond ordinary human experience. At those distances, temperatures could be so low that water ice behaves like rock. Carbon dioxide could freeze solid, nitrogen could freeze, methane could freeze. Any atmosphere the planet once had may have collapsed onto the surface long ago as frost. If Planet Y formed near the Sun and was thrown outward, it may once have been warmer. It may once have had internal heat, volcanic activity, maybe even gases around it. But once it was exiled to the outer solar system, everything changed. Sunlight weakened. Temperatures dropped. Volatile gases condensed. The surface froze. The planet became a tomb of its former self. If it once had an atmosphere, that atmosphere may now exist as frozen layers on the ground. Nitrogen frost, methane ice, carbon dioxide deposits, water ice harder than stone. The surface could be a mixture of rock, metal-rich material, ancient ice, and dark organic compounds created by radiation. In the outer solar system, surfaces are constantly bombarded by cosmic rays and faint ultraviolet radiation. Over billions of years, this radiation breaks apart simple molecules and helps form complex organic compounds called tholins. Tholins are reddish-brown materials found on many outer solar system bodies. They help give Pluto parts of its reddish color. They may coat the surfaces of distant icy worlds. If Planet Y has spent billions of years in the outer solar system, its surface may be dark red, brown, grey, or almost black. Not bright like fresh snow, not blue like Earth, but old, radiation darkened, frozen, weathered by space itself. Imagine standing on the surface. The first thing you would notice is the sky. It would not be blue, it would be black. If there is no significant atmosphere, there is nothing to scatter sunlight. On Earth, the sky is blue because air molecules scatter sunlight. On Planet Y, without air, the sky would remain black even during the day. The sun would hang above the horizon like a brilliant white star. The stars would remain visible. The Milky Way might stretch across the sky with incredible clarity. There would be no atmospheric shimmer, no clouds, no haze unless the planet has a thin temporary atmosphere from sublimating ice. The stars would not twinkle. They would burn as steady points of light in perfect silence, and the silence would be overwhelming. On Earth, silence is never truly silent. There is always something. Wind, insects, distant machines, your own breathing, your own heartbeat, the movement of air. But on an airless world, sound cannot travel through the atmosphere because there is no atmosphere. If you stood on planet Y in a spacesuit and struck a rock with a hammer, vibrations could travel through the ground and through your suit, but there would be no normal sound in the air. No echo, no wind, no rustling, no distant thunder, no waves, nothing. Just vacuum and frozen stone. The landscape would likely be covered in craters. Without wind, rain, rivers, oceans, or plate tectonics, impact scars can survive for billions of years. On Earth, ancient craters are erased by geology and weather. On planet Y, they may remain almost unchanged. A crater formed 4 billion years ago could still be visible. The surface would be a record of ancient bombardment. Every impact basin would be a memory of some collision from the solar system's youth. Some craters might be sharp, some softened by frost, some filled with frozen volatile deposits, some surrounded by rays of brighter material exposed by impact. There could be mountains. If planet Y has a rocky interior, ancient tectonic stresses may have created cliffs or ridges. If it once had internal heat, there may be old volcanic features. If it has enough ice, there may be cryovolcanic structures, places where water, ammonia, or other volatile materials once erupted like lava in extreme cold. This sounds strange, but we already know icy worlds can be geologically surprising. Pluto surprised scientists with young-looking surfaces and nitrogen ice plains. Enceladus shoots plumes into space. Europa likely has an ocean beneath its ice. Triton has geyser-like activity. The outer solar system is not always dead. It can be strange, active, and complex. So planet Y might be completely frozen and inactive, or it might preserve signs of an unexpected internal history we do not know. That is what makes it fascinating. Could planet Y have a magnetic field? Maybe, but it would depend on its interior. Earth has a magnetic field because of motion in its liquid metallic core. Mars lost its global magnetic field long ago. Mercury has a weak magnetic field. If planet Y has a metallic core and enough internal heat to keep part of it molten, it might have a magnetic field. But if it is too small and too old, its interior may have cooled and solidified. A spacecraft mission would be needed to know. Could planet Y have a thin atmosphere? Possibly, but it would likely be extremely thin. At such cold temperatures, many gases freeze onto the surface. However, some volatile materials might sublimate slightly when exposed to sunlight, creating a temporary or extremely thin atmosphere. Pluto has a thin atmosphere, even though it is far from the Sun. Triton also has a thin atmosphere. Planet Y might have something similar depending on its composition and distance. But compared with Earth, it would be almost airless. Its surface would be exposed to space. Cosmic radiation would strike the ground directly. Micrometeorites would slowly grind the surface over time. Charged particles from the solar wind, though weak at that distance, could interact with surface materials. Planet Y would be shaped not by weather, but by space itself. Now imagine its day. If planet Y rotates, it would have a day-night cycle, but the difference between day and night might not be dramatic. On Earth, day brings warmth and light. Night brings cooling and darkness. But on planet Y, sunlight is so weak that daytime might only be slightly brighter than night. The sun would illuminate the surface faintly, but not warm it much. The surface temperature might change only a little between day and night. If the rotation is fast, shadows would move across craters and frozen plains every few hours or days. If the rotation is slow, one side could face the sun for a long time before darkness returns. If the planet's axis is tilted, it could have seasons. But seasons on planet Y would not mean spring flowers or summer heat. They would mean tiny changes in weak sunlight across extremely cold terrain. Maybe frost migrates slightly from one region to another. Maybe some gases briefly sublimate when the sun is highest. Maybe surface brightness changes slowly over centuries. Everything would happen slowly. Because out there, time is different. A year on planet Y could last more than 1,000 Earth years, depending on its orbit. Imagine a season lasting centuries. A sunrise that matters not to plants or animals, but only to frozen nitrogen and methane. A world where geology sleeps. A world where the sun's return is barely enough to change the surface temperature. That is the kind of place planet Y might be. Could it have moons? This is one of the most exciting possibilities. Many distant worlds have moons. Pluto has 5 known moons. Haumea has moons. Makemake has a moon. Even smaller Kuiper Belt objects can have companions. If Planet Y has moons, they would be scientifically priceless. A moon's orbit could help measure the planet's mass accurately. The moon's composition could reveal whether it formed with the planet, was captured later, or was created by an impact. If Planet Y is a scattered inner solar system world, its moons might have formed through collisions or captures. If Planet Y is a captured rogue planet, any moons it brought with it would be even more fascinating. Imagine that. A rogue planet captured by the Sun, still carrying a moon from another star system. That moon would be one of the most extraordinary objects ever discovered. Even if Planet Y has no moons, that absence would also tell a story. Maybe it lost them during scattering. Maybe a close encounter stripped them away. Maybe it never had any. In planetary science, both presence and absence matter. Every detail is evidence. Now picture a spacecraft approaching Planet Y for the first time. After decades of travel, the spacecraft finally begins to resolve the world from a dot into a disk. Mission control waits as data comes in slowly across billions of miles. The first image is blurry, then clearer, then sharper. A horizon appears. Craters become visible. Bright patches of frost appear against darker terrain. Maybe a long canyon cuts across the surface. Maybe there is a giant impact basin covering one hemisphere. Maybe a small moon appears nearby, a tiny dark companion moving around the planet. Scientists stare at the images. For the first time in human history, Planet Y is no longer a theory. It is a place. That moment would be unforgettable, because the transformation from dot to world is one of the greatest moments in exploration. Before New Horizons reached Pluto, Pluto was a small, blurry object in our best telescopes. Then suddenly it became a real world with mountains, plains, haze, and complexity. Planet Y could give us the same feeling again, maybe even stronger, because Planet Y would be a planet we did not even know existed until recently. A world hidden in darkness. A world that may have shaped the outer solar system for billions of years. A world that might carry the memory of an ancient gravitational exile. What would it feel like emotionally? Lonely. That is the word. Planet Y would be one of the loneliest worlds in the solar system, far from the sun, far from the known planets, moving slowly through deep cold. No warmth, no bright day, no familiar sky, just ancient stone, frozen gases, cosmic radiation, and endless silence. And yet it would not be meaningless. It would be part of the story. It would carry information about the solar system's birth. It would hold clues about planetary migration. It might reveal whether rocky planets were scattered outward. It might even reveal whether our solar system captured a world from another star. A lonely planet can still be a powerful witness. That is what Planet Y may be. A silent witness to 4.5 billion years of cosmic history. If humans ever study it closely, we may learn more than just what it looks like. We may learn where it came from. We may learn how violent the early solar system really was. We may learn whether the outer solar system contains more hidden worlds. We may learn that our map was incomplete in ways we never imagined. And perhaps most importantly, we may remember that a world does not need to be bright to be important. Planet Y may be dark. It may be frozen. It may be silent. But if it exists, its gravity may already be shaping the edge of the solar system. And one day, its surface may become one of the most important landscapes ever seen by human eyes. A landscape of craters, ice, stone, radiation-darkened plains, a black sky, a distant sun, and the frozen memory of a story billions of years old. If Planet Y exists, then one question naturally rises above all the others. Why have we not found it yet? How can an entire planet hide in our own solar system? We have telescopes on mountains. We have space observatories above Earth's atmosphere. We have supercomputers. We have mapped distant galaxies. We have photographed black holes. We have discovered thousands of planets around other stars. So how could a planet orbiting our own sun still remain unseen? The answer sounds simple, but the reality is brutal. Planet Y would be far away. It would be faint. It would move slowly. And the sky is enormous. That combination makes it one of the hardest possible objects to find. A planet does not shine like a star. It does not produce visible light of its own. It becomes visible because sunlight hits its surface and reflects back toward us. That is how we see Venus, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and distant Kuiper Belt objects. But the farther a planet is from the sun, the less sunlight reaches it. And the less sunlight reaches it, the less light it can reflect back. This is the first problem. Distance kills brightness. Earth receives strong sunlight because it is 1 astronomical unit from the Sun. Neptune, at about 30 AU, receives sunlight roughly 900 times weaker than Earth. Pluto, depending on its orbit, receives even less. But Planet Y could be much farther than Pluto. If Planet Y is around 100 AU from the Sun, sunlight there would be about 10,000 times weaker than sunlight on Earth. At 200 AU, sunlight would be about 40,000 times weaker. Now imagine trying to see a small rocky world under that kind of faint illumination. It would not glow brightly. It would not stand out clearly. It would not look like a dramatic planet in a telescope. It would be a tiny dim point, a faint dot in a sky full of faint dots. And if its surface is dark, the problem becomes worse. Many objects in the outer solar system are not bright white balls of ice. Their surfaces can be darkened by radiation over billions of years. Cosmic rays and ultraviolet light can transform simple molecules into complex reddish-brown organic compounds. These materials, often called tholins, can make distant objects darker and harder to see. So Planet Y might be small, it might be far, it might be dark, it might reflect almost no sunlight. That alone makes detection extremely difficult. But brightness is only the beginning. The second problem is motion. Objects in the outer solar system move very slowly. Earth completes 1 orbit around the Sun every year. Neptune takes about 165 Earth years. A planet at 100 or 200 AU could take hundreds or thousands of years to complete 1 orbit, depending on its exact path. From Earth, that means Planet Y would barely crawl across the background stars. It would not streak across the sky. It would not jump dramatically from night to night. It would shift slowly. Very slowly. Astronomers find distant solar system objects by taking images of the same area of sky at different times. Then they compare the images. Stars and galaxies are so far away that they appear fixed. Solar system objects move slightly. That movement reveals them. This is how Pluto was discovered. Clyde Tombaugh compared photographic plates taken on different nights. The stars stayed still. 1 faint dot moved. That dot was Pluto. Modern surveys use digital cameras and computers instead of photographic plates and blink comparators, but the basic idea is the same. Find the moving dot. The problem is that Planet Y's movement may be extremely subtle. If images are taken too close together in time, it may not shift enough to identify confidently. If images are taken too far apart, the motion may become hard to connect because the object is so faint. Astronomers need the right timing, the right depth, the right sky coverage, the right software, the right follow-up observations. And even then, false signals are everywhere. A telescope image is not a clean picture. It contains stars, galaxies, cosmic ray hits, detector noise, satellites, asteroids, image artifacts, and countless faint sources. Some objects appear in one image and disappear in another. Some are real. Some are not. A cosmic ray hitting the detector can create a tiny bright spot that looks like a faint object. A background galaxy can be mistaken for a point source. A known asteroid can appear in the frame. A satellite trail can ruin part of the image. A faint object near a bright star can be hidden. The software must filter all of this. Then astronomers must verify the candidates. Most candidates are not new planets. Most are noise. Some are known objects. Some are small asteroids. Some are ordinary Kuiper Belt objects. Very few are truly unusual, and Planet Y, if it exists, would be buried inside that mountain of data. It would not arrive with a label. It would not say, "I am the hidden planet." It would simply be 1 faint moving dot among millions of detections. This is why discovery takes time. The third problem is the size of the sky. The sky looks like a dome above us, but for astronomers it is a huge, searchable surface. Even powerful telescopes can only image a portion of it at once. Some telescopes see deep but narrow, others see wide but not as deep. Finding a faint, distant planet requires both depth and coverage. You need to look deeply enough to detect it, but you also need to look across enough of the sky to include its location. That is hard, especially because we do not know exactly where Planet Y is. The possible warp in the Kuiper Belt can suggest what kind of planet might be responsible. It can suggest possible distances, masses, and inclinations, but it does not give a precise address. Planet Y might be above the main plane of the solar system. It might be below it. It might be in a crowded region of the Milky Way where background stars make detection harder. It might be in a part of the sky that has not been surveyed deeply enough. It might be near the direction of the sun from our viewpoint during certain seasons, making observation difficult. It might be hiding in plain sight in old data, too faint or too slow to have been recognized. That last possibility is important. Sometimes discoveries are not made by taking a new image. Sometimes they are made by reanalyzing old images in a new way. A faint object may already exist in archived survey data, but no one has connected the detections yet. Maybe Planet Y is sitting inside a database somewhere, waiting for the right algorithm, waiting for the right researcher, waiting for the right comparison. This has happened before in astronomy. Objects are sometimes discovered years after the images were taken. The data existed, but the interpretation came later. So when people ask, why haven't we found it yet? The answer is not that our technology is weak. The answer is that the search is extremely difficult. The outer solar system is dark. The object may be faint, the sky is huge, the motion is slow, and the signal is buried in noise. Now imagine the search like this. You are standing in a giant dark stadium. Somewhere on the far side of that stadium is a small black stone. Your job is to find it. You have a flashlight, but the beam only covers a small patch at a time. The stone does not glow. It reflects very little light. The floor is covered with other marks, shadows, trash, and small objects. Some things look like the stone but are not. Some things appear for a moment and disappear. You must scan the entire stadium carefully, again and again, comparing each section over time. That is already hard. Now make the stadium the size of the sky. Make the stone billions of miles away. Make it move so slowly that you can barely tell it moved. That is the search for Planet Y. This is why future surveys are so important. The Vera Rubin Observatory, for example, is designed to repeatedly scan huge areas of the sky. Its legacy survey of space and time will create a deep, repeated map of the visible sky. This kind of survey is exactly what astronomers need to discover faint moving objects. A hidden planet may not be obvious in one image, but if the same faint dot appears in multiple images and slowly shifts over time, the pattern can emerge. Motion reveals identity. Still, even with powerful surveys, there are no guarantees. Planet Y could be too faint. It could be too far. It could be in a difficult location. Its surface could be darker than expected. Its orbit could place it where current surveys are less sensitive. And if we do not find it, that does not immediately prove it does not exist. It only narrows the possibilities. Each failed search says something. If Planet Y were bright and close, we should have seen it. So maybe it is not bright and close. If it were large and reflective, it should stand out. So maybe it is smaller or darker. If it were in a well-surveyed region, it might already be known. So maybe it lies elsewhere. This is how science tightens the net. Searches do not only discover objects, they also eliminate possibilities. Over time, if no planet is found, the allowed space for Planet Y becomes smaller and smaller. Eventually, scientists may reach one of two outcomes. Either the planet is found, or the evidence becomes strong enough to say the Planet Y explanation is unlikely. Both outcomes matter. If Planet Y is found, the discovery would be historic. If it is not found, scientists must explain the Kuiper Belt warp another way. Maybe the warp is not real. Maybe the sample was biased. Maybe small bodies collectively caused the pattern. Maybe Neptune's past migration produced effects we do not fully understand. Maybe a passing star disturbed the outer solar system long ago. Maybe our models are missing something. A failed planet hypothesis would still lead to new science. That is important to understand. The search for Planet Y is not a waste if Planet Y does not exist. Because the search improves our map of the outer solar system. It finds new Kuiper Belt objects. It sharpens our understanding of distant orbits. It improves detection methods. It teaches us how to separate real signals from bias. Science does not move only by confirming exciting ideas. It also moves by eliminating wrong ones. But for now, the mystery remains open. Planet Y may be real. It may be hiding in darkness. And the reason we have not found it yet is not because the idea is impossible. It is because the object, if real, sits near the edge of what our surveys can detect. A dark world. A slow world. A distant world. A world that reflects almost nothing, moves almost imperceptibly, and waits in a sky too large to search easily. That is why it has remained hidden. Not because the solar system is small, but because it is enormous. Not because astronomers are not looking, but because the object may be incredibly difficult to see. Not because the mystery is weak, but because the darkness beyond Neptune is still one of the greatest frontiers in planetary science. And somewhere in that darkness, one faint moving point may eventually change everything. If Planet Y is discovered, the impact would be immediate. At first, the news would sound almost unbelievable. A new planet beyond Neptune, a hidden world in our own solar system, a body that may have been shaping the outer Kuiper Belt for billions of years. The announcement would spread across the world within hours. Science websites would publish breaking news. Space agencies would release statements. Astronomers would explain the discovery in interviews. Classrooms would discuss it. Documentaries would begin production. Social media would explode with diagrams, animations, speculation, and debate. People who had not thought about planets since school would suddenly look up at the night sky and wonder, how much else is still hidden? That would be the first change, a cultural shock. Because a new planet in our solar system is not just another scientific result. It is something people feel emotionally. The planets are part of humanity's shared imagination. They are among the first cosmic objects children learn. They appear in school books, museums, posters, films, and stories. Changing the planet list changes the mental map of reality. For many years, people learned 9 planets, including Pluto. Then Pluto was reclassified, and the official count became 8. That decision still remains emotionally powerful for many people. Some still say Pluto should be a planet. Others accept the dwarf planet classification. The debate became more than science. It became cultural. Now imagine a true new planet being confirmed. Not Pluto returning. Not a reclassification argument. A new world. A real planetary body that had been unknown. That would be one of the biggest astronomy stories of the century. But the cultural impact would only be the surface. The scientific impact would be much deeper. The first major change would be our understanding of the solar system's architecture. Right now, the official major planet system ends with Neptune. Beyond Neptune, we know there are dwarf planets, Kuiper Belt objects, scattered disk objects, detached objects, comets, and possibly other distant populations. But a confirmed Planet Y would show that the outer solar system contains at least one additional major planetary body. That would mean the solar system is more complex than the current 8-planet structure suggests. The map would need to change. The outer solar system would no longer be seen only as a debris field beyond Neptune. It would become a deeper planetary zone, a region where planets may still exist, a region where hidden worlds can shape the orbits of smaller bodies. This would force scientists to revisit models of solar system formation. If Planet Y is rocky, the question becomes even more important. How did a rocky planet end up there? If it formed close to the Sun and was scattered outward, then the early solar system had more terrestrial planetary embryos than the surviving planets we see today. That would mean Mercury, Venus, Earth, and Mars are not the complete story. They are only the survivors. There may have been other rocky worlds. Some collided, some were destroyed. Some fell into the Sun, some were ejected into interstellar space, and one may have been stranded beyond Neptune. This would make the solar system's early history feel more violent and more crowded. It would show that planetary formation was not a gentle process. It was a brutal selection event, a cosmic survival game. Planet Y would be evidence of that lost population, a frozen survivor from the era when planets were still fighting for stable orbits. If Planet Y formed in the outer solar system, the consequences would be different. That would challenge the standard idea that rocky planets form mainly in the inner region and icy giants form farther out. Scientists would need to explain how dense rocky material gathered so far from the Sun. They might need to revise models of material transport, planetesimal formation, collisions, and the distribution of solids in the early disk. This could change how we interpret planet formation around other stars. Because if our own solar system can create or preserve a rocky planet in the far outer regions, maybe other systems can too. And if Planet Y is a captured rogue planet, the discovery would be even more astonishing. That would mean our solar system contains a world that did not form here. A planet born around another star. A planet thrown into interstellar space. A planet later captured by the Sun. If proven, that would blur the boundary between solar system science and exoplanet science. We would have an extrasolar planet inside our own solar system. That sentence alone would transform planetary science. It would mean we could study a world from another star system without crossing interstellar distances. Of course, proving such an origin would be extremely difficult. Scientists would need strong evidence from the planet's orbit, composition, density, isotope ratios, and possibly moons. But even the possibility would inspire enormous research. The second major change would be the classification of planets. Would Planet Y officially become the 9th planet? That would depend on its properties and on the definitions used. To be considered a planet under the current International Astronomical Union definition, an object must orbit the Sun, be massive enough for its gravity to make it nearly round, and have cleared its orbital neighborhood. If planet Y is between Mercury and Earth in mass, it would almost certainly be round. It would orbit the Sun. The harder question would be whether it has cleared its neighborhood. At such large distances, the concept of clearing an orbit becomes complicated because orbital periods are long and the region is vast. Still, a Mercury-to-Earth mass body could be dynamically dominant in its region. If it meets the criteria, the solar system could officially return to 9 planets. But this time, the 9th planet would not be Pluto. It would be Planet Y, eventually given an official name. That naming process would become a global moment. What do you name a planet hidden in darkness? A planet that may have been lost? A planet that may have wandered? A planet that may have shaped the outer solar system unseen? The official name would likely come from mythology, following astronomical tradition, but public imagination would run wild before then. People would suggest names connected to darkness, exile, mystery, night, hidden worlds, forgotten gods, and cosmic wanderers. The name would matter culturally, but scientifically the object's nature would matter more. The third major change would be our understanding of the Kuiper Belt. If Planet Y is discovered in the predicted way, then the warp in the distant Kuiper Belt would no longer be just an anomaly. It would become evidence. The objects beyond Neptune would have acted like witnesses pointing toward the hidden planet. Their orbits would have told the truth before we saw the world itself. That would strengthen the idea that orbital patterns can reveal unseen planets. It would be a modern echo of Neptune's discovery. Uranus's orbit led to Neptune. The Kuiper Belt warp could lead to Planet Y. This would show again that gravity can reveal what light cannot. And it would encourage scientists to look for other hidden planets in other systems using similar logic. Debris disks around other stars often show gaps, warps, rings, or asymmetries. Astronomers already use these structures to infer unseen planets. If Planet Y confirms that a hidden planet can warp a distant belt in our own solar system, it strengthens that method. Our solar system would become a laboratory for interpreting distant planetary systems. The fourth major change would be technological and observational. Once Planet Y is discovered, telescopes around the world would turn toward it. Astronomers would want to know its exact orbit, its size, its brightness, its color, its rotation, its surface composition, whether it has moons, whether it has a thin atmosphere, whether it emits detectable infrared radiation, whether its surface changes over time. The discovery would trigger years of follow-up observations. Large telescopes would compete for time. Space telescopes might study it in infrared. Ground-based observatories would track its motion. Researchers would re-examine old survey images to see if Planet Y had been photographed before without being recognized. These older detections could extend the observation arc, helping calculate the orbit more precisely. The orbit would be one of the first priorities. A short observation arc only gives a rough path. To fully understand a distant planet's orbit, astronomers need observations over time. The more years of data, the better the orbit becomes. A precise orbit would tell us where Planet Y has been, where it is going, and how it interacts gravitationally with the rest of the solar system. It would also allow mission planners to dream, because once the orbit is known, a spacecraft mission becomes possible to design. The fifth major change would be emotional and philosophical. A new planet would remind humanity that the unknown is not only far away in distant galaxies, the unknown is also here, in our own system, in the place we thought we understood. That is powerful, because modern people often feel that the age of exploration is over. Earth has been mapped, the continents are known, the oceans have been crossed. Satellites photograph every country. GPS tells us where we are. Information feels instant. But space reminds us that exploration is not over. It has barely begun. A hidden planet beyond Neptune would prove that even our local cosmic neighborhood still contains major secrets, and that would inspire a new generation. Children would learn about the discovery and imagine becoming astronomers, planetary scientists, engineers, mission designers, data analysts, or astronauts. Universities would launch new research projects. Public interest in the outer solar system would surge. Planet Y would become more than a planet. It would become a symbol that there are still worlds to discover, still mysteries to solve, still blank spaces on the map. The sixth major change would involve future space missions. Once Planet Y is confirmed, the question would shift from, does it exist, to how do we study it. At first, telescopes would do the work, but eventually, scientists would want a spacecraft, a flyby, an orbiter, maybe one day a lander. That would begin a long new chapter in planetary exploration. A mission to Planet Y would take decades, but the scientific reward could be enormous. It could reveal the surface, composition, moons, magnetic field, atmosphere, and origin of a world that may have been hidden for billions of years. The discovery would therefore not be the end of the story. It would be the beginning. That is what great discoveries do. They answer one question and open 10 more. Planet Y would answer the question, is there a hidden planet causing the warp? But then it would ask, what is it made of? Where did it form? How old is its surface? Does it have moons? Does it have an atmosphere? Is it geologically dead? Was it scattered outward? Was it captured? Could there be more planets like it? Every answer would lead deeper. That is why the discovery would change so much. It would not simply add a planet, it would open a new frontier. And perhaps the most haunting change would be this. We would look at the night sky differently. Right now, when most people look up, they see stars. Maybe the moon, maybe Venus or Jupiter. They do not think about the invisible structure of the solar system beyond Neptune. But after Planet Y, the darkness would feel different. The outer solar system would no longer be an abstract idea. It would be a place where hidden worlds can still be found. A place where reality exceeded our map. A place where a planet moved for billions of years without a name. And once one hidden world is found, the obvious question becomes, what else is waiting? If Planet Y is discovered, humanity will not be satisfied with seeing it as a dot. That is never enough for us. A dot becomes a question becomes a mission. That is the pattern of exploration. When Pluto was discovered in 1930, it was only a faint point of light. For decades, even our best telescopes could show only limited details. Pluto remained mysterious, distant, and blurred. Then New Horizons flew past it in 2015. Suddenly, Pluto became a world. Mountains, plains, glaciers of nitrogen ice, a thin atmosphere, a heart-shaped region, complex geology. A place that had once been only a dot became real. Planet Y would follow the same emotional path. At first, it would be detected as a faint moving point. Then telescopes would refine its orbit. Then astronomers would estimate its size and composition. Then the public would ask the inevitable question, when are we going there? A mission to Planet Y would be one of the most ambitious journeys in human history. The distance alone would be overwhelming. If Planet Y orbits around 100 to 200 AU from the Sun, it would be far beyond Pluto. New Horizons took about 9.5 years to reach Pluto, and that was with a powerful launch and a gravity assist from Jupiter. Planet Y could be much farther. A spacecraft might take 20, 30, or even more years to arrive, depending on the trajectory, propulsion system, launch energy, and planetary alignments. This means a Planet Y mission would not be a quick project. It would be a generational mission. Scientists who design it might not be young when it arrives. Students who work on early planning might become senior researchers by the time data comes back. Some people who watch the launch might not live to see the encounter. That sounds difficult. But this is not new in space exploration. Voyager missions have lasted for decades. New Horizons took nearly 10 years to reach Pluto and continues exploring beyond. Great space missions require patience. Planet Y would demand even more. The first challenge would be power. Near Earth, spacecraft can use solar panels. Solar energy is abundant. Many missions rely on sunlight to generate electricity, but far beyond Neptune, sunlight is too weak. Solar panels would become enormous and inefficient. At Planet Y's distance, they would not provide enough practical power for a deep space spacecraft. So the mission would need nuclear power. Most likely, it would use a radioisotope thermoelectric generator, or RTG. An RTG is not a nuclear reactor. It does not use a chain reaction. Instead, it uses heat from the natural radioactive decay of material, such as plutonium-238. That heat is converted into electricity. Voyager used RTGs. New Horizons used an RTG. Curiosity and Perseverance on Mars use nuclear power sources. For a mission to Planet Y, an RTG would be essential. It would provide steady power in darkness. It would keep instruments alive. It would allow communication across billions of miles. But RTG power is limited. A spacecraft at Planet Y would not have huge amounts of energy. Every instrument would need to be carefully selected. Every system would need to be efficient. Engineers would need to manage power like a precious resource. The second challenge would be communication. At such distances, radio signals take a long time to travel. Light itself takes hours to cross the outer solar system. A command sent from Earth could take many hours to reach the spacecraft. A reply would take many hours to return. There would be no real-time control. Mission teams could not joystick the spacecraft like a drone. The spacecraft would need to operate autonomously. It would need to follow planned sequences. It would need to handle problems on its own. It would need to protect itself if something went wrong. During the close encounter, this autonomy would be critical. A flyby happens fast. New horizons past Pluto at high speed. The most important observations happened in a short window. The spacecraft could not wait for instructions from Earth. It had to execute commands that had been planned in advance. A planet-wide flyby would be similar, maybe even harder. The spacecraft would approach a world no one had ever seen up close. Scientists would have only limited knowledge of its size, rotation, moons, and environment. The spacecraft would need to aim cameras, collect spectra, search for moons, measure particles, and store data during a short encounter. Every second would matter. The third challenge would be data transmission. At enormous distances, the spacecraft's radio signal would be incredibly weak by the time it reaches Earth. Even using the largest antennas of the DeepSpace network, data rates would be slow. High-resolution images could take a long time to transmit. Maybe days, maybe weeks, maybe months for the full data set. This happened with New Horizons. The Pluto flyby lasted hours, but transmitting all the data back to Earth took many months. A Planet Y mission would likely be similar, possibly slower, depending on distance and spacecraft power. Imagine the emotional tension. The spacecraft has already passed the planet. It has captured the data. It is carrying images no human has ever seen, but the images are stored on board, traveling back to Earth as weak radio signals, bit by bit, across billions of miles. Scientists wait. The first low-resolution image arrives, then a better one, then another. Each image changes the world from mystery into reality. The fourth challenge would be trajectory. How do you reach Planet Y? The spacecraft would need a powerful launch. It might use a gravity assist from Jupiter or another planet to gain speed. Gravity assists are one of the most elegant tricks in spaceflight. A spacecraft flies close to a planet and uses the planet's motion and gravity to change its own speed and direction. It is like stealing a tiny amount of orbital energy from the planet. Voyager used gravity assists. New Horizons used Jupiter. A Planet Y mission would almost certainly need clever trajectory planning. But there is a problem. Planetary alignments matter. Jupiter, Saturn, Uranus, and Neptune are not always in convenient positions. A good launch window may happen only at certain times. Mission planners would need to calculate routes that balance speed, fuel, instrument safety, and arrival geometry. If the spacecraft travels very fast, it can arrive sooner. But a faster flyby gives less time for close observations. If the spacecraft travels slower, it may get better observation conditions, but the mission takes longer. If scientists want an orbiter instead of a flyby, the challenge becomes much harder. An orbiter must slow down when it arrives. That requires fuel. A lot of fuel. The farther and faster the spacecraft travels, the more difficult it is to break into orbit. A flyby is realistic. An orbiter is much more ambitious. A lander is even more extreme. So the first Planet Y mission would probably be a flyby. It would be designed to answer the most important questions quickly. What does the planet look like? How big is it? What is its surface made of? Does it have moons? Does it have rings? Does it have an atmosphere? Does it have a magnetic field? Is it geologically dead or surprisingly active? The spacecraft would carry cameras. A visible light camera would capture surface images. A near-infrared spectrometer would identify ices and minerals. An ultraviolet instrument might search for a thin atmosphere. A magnetometer could detect any magnetic field. A dust detector could measure particles in the environment. A plasma instrument could study interaction with the solar wind. A radio science experiment could help measure mass and gravity. Every instrument would be chosen carefully. Spacecraft have limits. Mass limits, power limits, data limits, cost limits. Engineers and scientists would argue over every kilogram, every watt, every observation. That is how missions are built, not with unlimited dreams, but with difficult choices. Now imagine the mission timeline. First, Planet Y is discovered. Then astronomers observe it for years to refine the orbit. Then mission proposals begin. Scientists write studies. Engineers examine possible spacecraft designs. Agencies consider budgets. Committees review mission concepts. If approved, the spacecraft enters development. Instruments are built. Systems are tested. Software is written. The spacecraft is assembled. The launch vehicle is selected. The trajectory is finalized. Then, one day, the spacecraft launches. A rocket rises from Earth, carrying a machine designed to visit a world hidden for billions of years. The spacecraft leaves Earth. It passes the Moon. It enters interplanetary space. Maybe it flies past Jupiter for a gravity assist. Jupiter fills the camera view for a short time. Then Jupiter shrinks behind it. The spacecraft continues outward. Years pass. It crosses Saturn's orbit, then Uranus's orbit, then Neptune's orbit. The Sun becomes smaller. The solar system becomes darker. The spacecraft keeps going. Decade after decade, it travels through cold emptiness. Then, finally, Planet Y appears ahead. At first, just a point, then a dot with shape, then a disk, then a world. The spacecraft begins its final observation sequence. Mission control on Earth cannot command it in real time. The instructions were uploaded long before. The spacecraft turns itself. It points its instruments. It begins imaging. The first close pictures reveal a surface never seen before. Maybe it is covered in craters. Maybe one hemisphere is darker than the other. Maybe bright frost fills lowlands. Maybe there are giant cracks across the crust. Maybe there is a huge impact basin. Maybe a moon rises above the horizon. Maybe the planet has a thin haze. Maybe it is more active than anyone expected. Or maybe it is ancient, dead, and perfectly preserved. Either result would be priceless. The spacecraft races past. Closest approach lasts only a short time. Then Planet Y begins to shrink behind it. The encounter is over. But the data is just beginning to return. For months, maybe years, the spacecraft transmits its findings back to Earth. Scientists analyze the images. They map the surface. They count craters. They identify minerals and ices. They calculate density. They search for moons. They look for signs of atmosphere. They compare the data with formation models. And slowly, the story of Planet Y becomes clear. Was it born near the Sun? Was it scattered outward? Did it form in the outer solar system? Was it captured from another star? The spacecraft may not answer everything, but it would transform the question. Before the mission, Planet Y would be a mysterious, distant body. After the mission, it would be a place, a landscape, a world with history. That is the true power of exploration. It turns points of light into places. It turns speculation into geography. It turns mystery into knowledge. And one day, if humanity continues exploring, a second mission may follow. Maybe an orbiter, maybe a lander, maybe a probe that studies the surface directly. A lander on Planet Y would be one of the most extreme machines ever built. It would descend in near darkness. It would need nuclear power. It would need heaters to survive the cold. It would need instruments that work in vacuum and extreme temperatures. It might drill into frozen material. It might measure seismic activity. It might test surface chemistry. It might capture a panorama of a black sky, a distant sun, and a frozen horizon billions of miles from Earth. That image would be historic, a photograph from the surface of a hidden planet. The kind of image that would make humanity stop and stare. Because it would show us something profound. The solar system is not just a diagram. It is made of places, real places, some warm, some violent, some beautiful, some dead, some hidden. Planet Y may be one of those hidden places, and a mission there would not only study a planet, it would prove something about us, that humans can commit to knowledge across generations, that we can build machines to cross darkness, that we can care about a frozen world we may never visit in person. That curiosity can survive distance, difficulty, and time. A mission to Planet Y would be expensive, difficult, long, risky. But that is true of every great exploration. The reward would be a new chapter in human understanding. And maybe when the first close-up image arrives, people around the world would feel the same thing. Because somewhere beyond Neptune, a world that had existed in darkness for billions of years would finally be seen. And in that moment, Planet Y would stop being a hidden possibility. It would become part of humanity's known universe. And now we return to the question that started everything. Is Planet Y real? Somewhere beyond Neptune, in the cold darkness where sunlight is weak and time moves slowly, is there truly another world hiding from us? A rocky planet? A frozen survivor? A hidden body whose gravity may be bending the distant Kuiper Belt? Or is Planet Y only a shadow created by incomplete data, a pattern that looks meaningful now but may disappear when more objects are discovered? That is the honest truth of this mystery. Planet Y is not confirmed. It may exist, it may not, but the search itself tells us something powerful. It tells us that the solar system is still not fully known. For centuries, humans looked at the night sky and believed they understood what they were seeing. The planets were wandering lights. The stars were fixed points. The heavens seemed eternal and perfect. Then telescopes changed everything. The moon became a world with mountains and craters. Jupiter became a planet with moons. Saturn revealed rings. Uranus was discovered. Neptune was predicted through mathematics. Pluto was found as a faint moving point. Then Pluto itself became part of a larger story when the Kuiper Belt revealed that the outer solar system was filled with icy worlds. Every time humans thought the map was complete, the universe expanded it. And now, once again, we may be standing at the edge of another expansion. A hidden world may still be waiting beyond Neptune, not because the solar system is magical, not because scientists are careless, but because space is enormous, because darkness hides faint objects, because distant planets move slowly, because the outer solar system is harder to explore than most people imagine. Planet Y, if it exists, would not be bright and obvious. It would not shine like a star. It would not cross the sky quickly. It would sit almost motionless against the background of distant stars, reflecting only a tiny amount of sunlight from billions of miles away. For years, maybe decades, it could hide in plain sight. A faint dot in a database. A weak signal in an image. A moving point that no one has connected yet. And that is what makes this mystery so haunting. The planet may already have been photographed. Maybe its light has already touched a telescope sensor. Maybe it is sitting somewhere in archived survey data, waiting for someone to notice its motion, waiting for the right software, waiting for the right researcher, waiting for the right moment. This has happened before. Astronomy is full of discoveries hiding in old data. A telescope captures more than humans can immediately understand. Years later, someone returns to the images with a new question, a new method, or a better model, and suddenly a forgotten dot becomes important. Maybe Planet Y is like that. Maybe it is already in the record. Maybe the solar system has already whispered its secret, but we have not understood the message yet. Or maybe it is not there at all. Maybe the warp in the Kuiper Belt is not caused by a planet. Maybe the current data is incomplete. Maybe the sample of distant objects is too small. Maybe observational bias has created an illusion. Maybe Neptune's ancient migration left a pattern we have not fully modeled. Maybe a passing star disturbed the outer solar system long ago. Maybe a hidden population of smaller bodies is responsible. Maybe the answer is something no one has thought of yet. That is why this story is not only about Planet Y, it is about the way science works. Science is not the art of being certain too early. Science is the discipline of doubt. It begins with a mystery. Then it gathers evidence. It builds models. It tests predictions. It searches for alternatives. It corrects itself. It rejects weak explanations. It follows the data, even when the data leads somewhere unexpected. Planet Y is not important only if it exists. It is important because it forces us to ask better questions about the outer solar system. Why are distant objects arranged the way they are? How did Neptune shape the Kuiper Belt? How much mass is hidden in the outer solar system? Could there be more undiscovered planets? How often are planets scattered from their birthplaces? Can stars capture wandering worlds? How complete is our map of the sun's kingdom? These questions matter, because the solar system is not just a collection of objects. It is our origin story. Earth did not appear separately from everything else. It formed inside the same disk that created the planets, moons, asteroids, comets, and Kuiper Belt objects. The story of Planet Y, if real, is connected to the story of Earth. The same early chaos that may have thrown Planet Y into darkness also shaped the world beneath our feet. The same gravitational forces that scattered small bodies may have delivered water to Earth. The same ancient disk that created distant icy objects also created the material from which life eventually emerged. When we study the outer solar system, we are not studying something separate from ourselves. We are studying the larger history of home. That is why a frozen planet beyond Neptune matters, because it may carry a memory Earth has lost. Earth is alive and active. Its surface changes, its crust recycles, its atmosphere evolves, its oceans move. Life transforms it. Earth is beautiful, but it is not a perfect archive of its own beginning. A distant frozen world may preserve what Earth erased. Planet Y, if it exists, may be a time capsule. Its craters may remember ancient impacts. Its surface may preserve chemical signatures from the early solar system. Its orbit may record a violent gravitational event. Its composition may reveal whether it was born near the sun, formed in the outer dark, or came from another star system. That is the incredible possibility. One hidden planet could answer questions about billions of years of history. But first, it must be found. The search will continue. Telescopes will scan the sky. Astronomers will measure distant objects. Computers will compare images. New surveys will discover more Kuiper Belt bodies. Models will improve. Some ideas will grow stronger. Some will collapse. And slowly, the mystery will narrow. This is how the unknown becomes known. Not all at once, not with one dramatic moment every time, but through thousands of careful observations, through patient work, through nights of telescope time, through data that looks boring to most people but may contain the next great discovery. Somewhere in that data, maybe there is a faint moving dot, a dot that does not belong to any known object, a dot whose orbit is too distant, a dot whose brightness suggests a world larger than an ordinary Kuiper Belt body, a dot that, after months or years of follow-up, becomes undeniable. Imagine that moment. An astronomer notices the candidate. At first, they are cautious. It could be noise. It could be an artifact. It could be a known object with imperfect data. They check again. The object appears in another image, then another. It moves slowly. Its path is real. They calculate a preliminary orbit. The numbers are strange. Too far, too large, too important. Other telescopes are asked to confirm it. More observations come in. The orbit sharpens. The estimated size grows clearer. The possibility becomes stronger. Then, finally, the announcement is made. A new planet-like world has been discovered beyond Neptune. If that day comes, the world will stop for a moment. People will look up at the night sky with a new feeling, because the sky will no longer feel fully known. It will feel alive with hidden structure. And even though no human eye can see Planet Y directly from the ground, people will know it is there. A real world. A world that existed before we named it. A world that moved in darkness while all of human history unfolded. A world that waited beyond the edge of our maps. And then the next chapter would begin. Scientists would study it from Earth. They would measure its color. They would search for moons. They would estimate its density. They would model its orbit. They would ask where it came from. Then, eventually, someone would propose a mission, a spacecraft to Planet Y, a machine built by human hands, launched from Earth, sent outward beyond the known planets toward a world hidden for billions of years. That mission would take decades. It would be difficult. It would be expensive. It would require patience across generations, but the reward would be unforgettable. The first close image of Planet Y, a surface never seen before, a horizon under a black sky, a distant sun shining like a cold star, craters, frozen plains, dark organic material, maybe mountains, maybe a moon, maybe signs of a history stranger than anything we predicted. At that moment, Planet Y would stop being an idea. It would become a place. And that is what exploration does. It turns mystery into geography. It turns a dot into a world. It turns darkness into knowledge. But even if Planet Y is never found, the story will still matter, because the search will have expanded our understanding. It will have found new distant objects. It will have improved our models. It will have tested our assumptions. It will have reminded us that science is not only about answers, it is also about asking the right questions. And sometimes the greatest value of a mystery is not that it gives us what we expected. It is that it forces us to discover something else. Maybe Planet Y will be real. Maybe it will not. But the outer solar system will remain mysterious either way. There are still objects we have not found. There are still orbits we do not understand. There are still ancient histories buried in ice. There are still regions where sunlight is faint and our maps are incomplete. The solar system is not a finished story. It is an open book. And we have only read the first chapters. This is the final lesson of Planet Y. The universe does not become smaller when we learn more. It becomes larger. Every discovery opens another door. Every answer reveals another question. Every new world reminds us that reality is deeper than our imagination. Humans have always looked up and wondered. Ancient people saw gods in the sky. Sailors used stars to cross oceans. Astronomers used telescopes to reveal planets. Mathematicians used gravity to predict Neptune. Engineers sent spacecraft to worlds no human could reach. And now, astronomers may be reading the faintest clues in the frozen darkness beyond Neptune, asking whether another planet is waiting there. That desire to ask, to search, to understand, that is one of the most human things about us. We are small. Earth is small. Our lifetime is short, but our curiosity reaches across billions of miles. It reaches into darkness. It reaches toward worlds we may never touch. It reaches toward Planet Y. So, the next time you look at the night sky, remember this. You are not looking at a finished map. You are looking at a mystery still unfolding. Beyond the Moon, beyond Mars, beyond Jupiter, beyond Saturn, beyond Uranus, beyond Neptune, beyond Pluto. Somewhere in the darkness there may be another world, a hidden planet, a frozen survivor, a silent sculptor of the Kuiper Belt, a world that has no official name, a world that no spacecraft has seen, a world that may have waited billions of years for us to notice it. And whether Planet Y is real or not, the search for it proves something powerful. We are still explorers. The frontier is not gone. The unknown is not empty. The solar system still has shadows. And inside those shadows, secrets remain. Maybe one day, one of those secrets will move across a telescope image, just a faint dot, barely visible, almost nothing, but enough. Enough to change the map, enough to change the story, enough to remind us that the universe is still full of hidden worlds. Until that day, Planet Y remains suspended between science and mystery. Not proven, not impossible, not discovered, not dismissed. A question orbiting in the dark. And sometimes the greatest discoveries begin exactly that way, with a question, with a pattern, with a silence, with something unseen pulling on the edge of everything we thought we knew. That is the mystery of Planet Y, and that completes the journey to the hidden frontier beyond Neptune.